Now, however, let us try to determine to what extent the commonly used construction of phylogenetic trees based on substitutions, that is, base replacement at individual positions of mitochondrial DNA codons, has its justification. Is this merely an invention of fanatical evolutionists? Despite the obvious lack of factual confirmation, perhaps, according to evolutionists, the theory of evolution finds its key justification precisely here. After all, we are not dealing with people who are incapable of thinking. So let us see how it looks. So once again, let us look at the comparison of codons from one of the mitochondrial DNA genes of humans and mice that was discussed earlier. Let us remember that substitutions occur at corresponding codon positions. These include both transitions and transversions. The most straightforward thing we can do now is to count transitions and all transversions. We obtain two values, the total number of transitions and the total number of transversions occurring at the corresponding codon positions between human and mouse genes. On the right, we can see a table showing the number of transitions and transversions along all 13 mitochondrial DNA genes for several selected mammals. We considered representatives of several primate species. Here we can see the gibbon, orangutan, gorilla and chimpanzee. The comparison also includes humans and mammals much less similar in structure to humans than primates, such as bovines and the mouse. In the blue cells, at the top of the table, along the diagonal, the transitions between these mammals are shown, that is, each species compared with every other. And in the orange cells, we see a corresponding summary of the transversions, so we can now select the mammals we want to compare. For example, a bovine and a chimpanzee. To read the transitions, we select the bovine from the yellow column and then the chimpanzee from the yellow row at the top, and then read the transitions value at the intersection of these selected cells. To read the transversions, we similarly locate the chimpanzee in the yellow column and the bovine in the yellow row, and then read the transversion value at the intersection of these cells. What can we observe in this table? First of all, we learn a key piece of information. Specifically, we notice that both the number of transitions and transversions between the representative mammal with the highest number of substitutions and the other mammals with fewer substitutions remain at a similar level. For example, between the mouse and the other mammals, the number of transitions remains at a similar level around, say, 1500, and the number of transversions is around 1900. This pattern repeats for all mammals that have the highest number of substitutions within a given group. What does it imply? It immediately suggests the possibility of creating a tree of connections in which changes could occur from common nodes, that is, from shared ancestors or shared designs. I will try to illustrate this based on a substitution tree of so-called primates. Namely, between the gibbon and the other mammals, the number of transversions remains around 500 and the number of transitions around 1500. So, for simplicity, let's assume these exact values and call them the distance. In other words, the distance of changes from the gibbon to all other primates has a constant value of 500 and 1500. A similar situation occurs for the orangutan in relation to the gorilla, human and chimpanzee. However, the distance of these changes remains at 400 and 1400. Next, the gorilla in relation to the human and the chimpanzee, as well as the human and the chimpanzee. Let us first consider only the case of the orangutan and the chimpanzee for transversions, because the distance between the gibbon and the orangutan, as well as the gibbon and the chimpanzee, is roughly the same, while the distance between the orangutan and the chimpanzee is clearly smaller. This means that some of the changes observed between the gibbon and the chimpanzee and between the gibbon and the orangutan must have occurred outside the changes seen between the orangutan and the chimpanzee, indicating the presence of a common ancestor or project for the orangutan and the chimpanzee. A similar situation occurs with the changes between the gorilla and the chimpanzee, as well as their constant distance from the orangutan. Moving further, we see an analogous situation with the arrangement of the gorilla and the human and chimpanzee. In this way, we can outline a phylogenetic tree as shown in the figure, along with the corresponding distances indicated on each branch. Ultimately, based on our substitution table, we can construct a tree as shown in the figure on the left. However, there is one exception: bovine, whose distance from the other mammals is slightly smaller. What conclusions can be drawn from this? First, each of the selected groups of mammals may descend from a common ancestor or originate from a common design. Second, similar amounts of changes occurred from the common ancestor or from the common project. Here we can see similar distances illustrated as branch lengths. An exception in our tree is the bovine, whose distance from the other mammals is slightly smaller. Similar distances may suggest the passage of time from the common ancestor, although both the assumption itself and the specific time frame are, of course, already a matter of interpretation. What these distances definitely indicate is a similar number of changes, certainly linked to the adaptation of protein functions to changes in the complexity of organismal functions. The assumption of constant and purely random changes in currently non-coding fragments can only be considered a simplified interpretation. We will address this topic in a later stage of the presentation.